So, dear students, welcome back. In this lecture, we shall carry on with the examples of some more examples of functors. So, in the previous lecture, we have seen many interesting examples of functors. So, let us do some more. So, first is the Powerset functor, the covariant Powerset functor. So, covariant Powerset functor. Set functor. So this is from the category of set to the category of set. So P from set to set is defined by so P from a set A to a set B. Suppose I have a morphism, a map F. So this Powerset functor, it assigns each set to its power set. So P of A goes to P acting on this set A goes to power set of A. P acting on this set B goes to power set of B, and this F goes to P of F. So where P of A is the power set of A. Power set, you know, the set of all subsets of A, is the power set of A, and for any X subset of A, means X belonging to power set of A, this PF of X is F of X. Where what is F? This F of X is the image of X under F. So obviously it is a subset of B. Is the image of X under F. So we see that this covariant power set mapping, it's a functor actually, because it respects the composition as well as the identities. So suppose P, so I have suppose X to I, suppose A to B, I have F, and B to C I have, say, a mapping G. This is the mapping G composition F, and the power set, this functor P, it sends it to power set of A, power set of B. So this is PF, and then C goes to power set of C, and this mapping is PG, and then you have PG composition F. So it respects the composition because P of G composition F of any X, where X is a subset, this is A, where X is subset of A. So X here is a subset of A belonging to the power set of A. So by its definition, it is F composition Gx, means it is a subset of C. Sorry, it is G composition F. G composition F X means it is a subset of C. Okay, and G composition Fx, so by definition of composition of maps, so it is G of F of X, but F of X is what? By definition of this functor, this mapping P, it is G of this Pfx. Okay, and G of this thing is what? G of this thing is actually P of G of P of F of X. Okay, P of G of P of F of X. So P of G of P of F of X. Okay, so this you can write as P of G composition P of F of X. So this means you are through. So P of G composition F is same as P of G composition P of F. So this mapping P respects the composition. Moreover, if third condition, if I have A to B a mapping F and B to B, suppose the identity on B, so P of this is what? This is P of A to P of B to P of B. So this is P of F, this is P of identity of B. Now for any X which is a subset of A, if I compose this P of identity on B with P of F, so P of identity on B composition P of F of this X is going to be P of identity on B. Now apply P of F of X. P of F of X is what? It is going to be F of X. But this P of identity on of B on F of X, this would be what? This would be actually identity of B of F of X. Identity of B of F of X. But identity of B composed with F is same as F. So this is F of X. This is F of X. And F of X is what? F of X is nothing but PF of X. So thus we have that P of identity on B composition P of F is P of F. Similarly, if I composed any P of G with P of identity on B from right, I would get back P of G, where G is any mapping from B to C. So thus, I can now say that P of identity on B is same as identity on P of B. So thus this P from set to set is the covariant power set functor. Now I can just take the dual situation of this as follows. So I will not write the proof, I will just give the statement, and proof would be exercise for you to verify. Similarly, you can define the contravariant power set functor, not from set but from set opposite to set. So the category set opposite to the set category. So prove that, so the exercise, prove that Q from set opposite to set defined by so Q is from A to B. Suppose in set opposite I have F. Okay, so it goes to QA, the power set of A, QB, the power set of B, and this is QF. So where for each X subset of A, now this QFX, this arrow, it is defined as the reverse image of X, the inverse image of X, F inverse X. The pre-image of X, the pre-image of X under F from B to A. So we must also note that this F is from A to B, but F is from A to B in the set opposite category. So in set category, it would be from B to A. Okay. So is a functor. So this Q defined in this way is a functor. So if it is a functor, we call it as contravariant power set functor, called as the contravariant power set functor. Power set functor. So this is an exercise for you students. Now I move on to discuss with you some more examples. So this is example number 7. So again this is from set to set. This functor is from set category to the set category. So how do I define this? So for any positive integer n, for any positive integer n, I call it the nth power set functor, the nth power functor, the nth power functor. I denote it by Sn. Sn is from set to set, from set to set, and is given by, it is defined by Sn. Suppose I have a set X and a set Y. and f is a mapping from x to y. So so what does this, how it respects the domain and codomain? Sn acting on x, so Sn acting on x sends it to xn, and where xn is the set of n tuples of the elements of x, and similarly it sends y to yn. Again yn is the set of n tuples of y, so n copies of y. So but f goes to fn. Now what is this fn? Where fn acting on any element of this xn, so say it is x1, x2, so on xn, it sends it to fn, sends this element here as f of x1, because f of x1 is a member of y1. Similarly f of x2 is a member of y2, and so on. So obviously the image would be a member of yn. F of x1, f of x2, so on f of x. Now you can easily verify that the other two axioms, they are true, means the preservation of composition as well as identities. See how. So if you take Sn of G composition F, so by definition it would be G composition Fn and G composition F whole n acting on any member, say of xn, say it is x1, x2, so on xn. So it would be what? It would be G composition f x1, so on G composition f xn, which is same as G of f of x1, so on G of f of xn. Okay. So G of f of x1, now G of f of x1, so let it be, say, equation star. Now if you take Sn of G composed with Sn of f, so by definition it is what? It is Gn composition Fn, and for any element of xn, if you apply on this x1, x2, so on xn, so you can easily see that it is same as, it is also G of f of x1, so on G of f of xn, say double star. So star and double star are same. So what does it mean then? So it then means that Sn of G composition F is same as Sng composition Snf. So the composition is preserved. Thirdly, you can see that the identities are also preserved. So Sn of, say, x to y f, y to y identity and y, and Sn sends this to xn to yn fn, and yn to yn identity and yn whole power n. And if you compose identity and y whole power n with f power n, you would easily see that it is f power n. Similarly, if I composed any g raised to power n with identity of y whole power n, I would get back g raised to power n. So this means I can conclude that identity and y whole raised to power n is what? It is actually identity on yn. Okay, so therefore this S is a functor. So this is called the nth power set functor. Now the next example is from linear algebra. It is called duality functor for vector spaces. Duality functor for vector spaces. So duality functor for vector spaces. So it is from vec opposite to vec, where vec is the category of vector spaces over a field. So let f be from vec opposite to vec. So vec is the category of, so vec is what? Vec is the category, I take the category of real vector spaces, for example, the category of all vector spaces over the real field R. So vec opposite is the opposite category of. So suppose, so what does this functor do? This f, so suppose I have a, so vec, it is from vec opposite to vec. So f associates with any vector space V, its dual V cap. You know the dual of a vector space. It is the vector space of all linear functionals. So V cap is what? V cap is actually home VR. Home VR. Set of all linear transformations, the vector space of all linear transformations, or linear functionals you can say, with operation as pointwise addition and scalar multiplication. And it has, so any object, any V goes to V cap, and any vec opposite morphism F from V to W to F cap from V cap to W cap, where F cap, where f cap of any G, so G is in V cap, so f cap of G is defined as G composition F. Okay, so what does this functor do? So if I see with the help of diagram, so you see here, so actually this is the situation here. So here I have the category vac opposite, here is the category vac, here again is the category vac. Suppose I have V and W elements in vac opposite, and F is an arrow from V to W, but in vac the direction of arrow would be opposite, so F would be arrow from W to V in F. So what does, in other words, you can say that if I have a linear transformation from W to V in a vector space category, then this F just flips the role of V and W. So this F on this, or you can say F on this, first introduces V cap, the dual of V, and then W cap, and then F cap. Okay. Now you can easily see that this satisfies the axioms of a functor. So it assigns to each vector space its dual vector space, and to each morphism F a morphism F cap, which is defined in this fashion. So let us see the other two axioms, the preservation of composition as well as identities by this vac F, or this functor F. So again I would first come from vac opposite to vac in order to understand the situation. So here you have vac opposite category, here you have vac, and the resultant is again in vac. So in vac opposite I have V to W say F, W to Z say G, and then it is G composition F. But in vac you have the reverse situation. So F would be from W to V. So W to V I have F, and G would be from W to Z. So the direction of the arrows would be changed. G, and then here so no, it would be from Z to W, because in vac it is from W to Z, so here it would be from Z to W. Okay, Z to W, and then W to V. Then I have composition which I call F composition G. It is from Z to V. Here it is from V to Z, so here it is, in vac it would be from Z to V. So what does this functor do? It maps V to V cap, W to W cap, Z to Z cap, the dual. And if I have an arrow from W to V, that is F, then I have F cap from V cap to W cap. So F cap from V cap to W cap. So I have an arrow from W to from Z to W in G, but the resultant arrow would be from W cap to Z cap, that is G cap. Now I have an arrow F composition G from Z to W. F composition G cap would be from V cap to Z cap. This is F composition G whole cap. Now I have to see that, and this is what? F cap is nothing but F of F. G cap is nothing but F of G. This is nothing but F of F composition G. Okay? Sorry, F of G composition F. F of G composition F. Okay? F of G composition F. Now F of G composition F, here is what? F composition G cap. Okay. Now for any H in V cap, now this F composition G cap is actually from V cap to Z cap. So I have to choose any H in V cap and apply on this. So F composition G whole cap of H. Okay. By definition of this, it is H composition F composition G. But I can write it as H composition F composition G. Now if we see this H composition F composition G with the definition of this functor F acting on arrows, it is nothing but G cap of H composition F. Okay, and H composition F is what? F cap of H. So it is G cap of F cap of H. Okay, so you can see that it is G cap composition F cap of H. Okay, so which is nothing but, so this means you can say that this is nothing but F of G composition F of F, F of F. So we can say that F of G composition F is same as F of G composition F of F. So F respects the composition. Similarly, a small exercise, a small verification would show